We can move closer to a realistic model of simple harmonic motion by adding damping. If we're talking about a mass and a spring, friction between the table and the block would be a damping force. For a pendulum, we could use air resistance. For a car suspension, which is springs and shock absorbers, the shock absorbers are the damping force, or provide the damping force. We can model this damping force rather than using friction, which is a little bit of a mess. We can model this damping force like our simplest formula for air resistance was and say that the force is negative BB. We put this in Newton's second law and get what again looks very simple, negative kx minus BV equals max. But again, this is a differential equation, not an algebraic equation. And this is a worse differential equation. This is a bigger mess. If we solve this, or have somebody solve this from the math department, we get that x as a function of t is amplitude times this exponential damping factor times, again, a cosine. Notice that instead of omega, things have changed a little bit. Omega would be just square root of k over m. But here the addition of damping is actually changing the fundamental period. This, instead of just a regular sine wave or cosine, we get something like this. We get this damped oscillation that will eventually die out. We can then talk about this as being overdamped, underdamped, or critically damped. If it's overdamped, this would be a case where the shock absorber is much more powerful than the springs. If you've seen a screen door, self-closing door, if you've ever seen one where you walk out and it closes but it takes a very long time to close behind you, that would be an overdamped system. An underdamped system would be if you walk out the door and it slams behind you immediately and bounces a couple of times before it finally stops. Critically damped door would be the perfect balance between these, and it will actually come to rest quicker than anything else. That doesn't mean it'll hit the frame first, because the underdamped model will slam first, but it won't finish shutting before the critically damped one does. Then we can look at the damped-driven simple harmonic oscillator. So here you could imagine we have an external influence pushing the mass back and forth. For example, you could be grabbing the mass attached to the spring and shock absorber and just slide it back and forth by hand. If you do this, this is called the driving frequency, however fast you choose to move it back and forth. And the mass moves at that frequency no matter what the natural frequency it would be if you let it go. It'll still move at the driving frequency instead. However, if those two things get close to each other, if the driving frequency is very close to the natural frequency, you end up with what's called resonance. Little kids figure this out right away when they're pushing someone on a swing, which is a good approximation of a simple pendulum. If they time their pushes just right, if they match the natural frequency of the swing, they can get very, very large amplitudes built up pretty quickly, and these can be damaging. For example, you can get your finger wet running around the edge of a wine glass and it'll make a noise. If you record that noise and then play it back much louder, the glass will start to vibrate. It'll become a damped-driven harmonic oscillator. If it's loud enough, since it's at resonance, you will shatter the glass. You can see the same thing happen in buildings during earthquakes. There was an earthquake in Mexico City in 1985 where tall buildings and short buildings seemed to get through just fine, but medium height buildings happened to have natural frequencies right about that of the earthquake, and they were destroyed, at least some of them. The other effect that this has that has to be considered, if you're building a skyscraper, the steel is going to flex a little bit in the wind, and in general, the top of a very tall skyscraper may move back and forth several meters at a time in a windstorm, which is enough to make people seasick. And the tall floors are where people are paying the most, and they don't want to pay to be seasick. So sometimes you have what's called a tuned mass damper added to the building, and this is just a large mass that's moved hydraulically back and forth to cancel the building's motion and give it a much smoother ride.